Hi, so this is the third and the final lecture for the first chapter on measurement for H2 physics. Okay, so we'll start with this schematic of a helicopter. So how does a helicopter ascend? Okay, now first of all, let's talk about the forces that acts on the helicopter. Uh, I'm sure you know there's the weight, and when the rotor that is shown here in black, it turns, it generates lift. Okay, it pushes the air down and the air will push the rotor blade up. So it generates an upward lift. Okay, so when L is equals to W, the helicopter will hover. But if L is greater than W, then the helicopter will extend. Okay, you'll move upwards. Okay, so that's simple enough. Now, but the purpose of a helicopter is not to just move up and down, it's to move forward. So how does the helicopter move forward? Now, let's look at this diagram. Let's look at this picture. Normally, when helicopter move forward, it's tilted like this. Okay, you will not see a helicopter moving forward and the form and shape is in this way. Okay, where the lift is up, the weight is down because there's no force forward. But what if the rotor is tilted or the entire helicopter is somehow tilted in this form? What do we have? The weight will still be pointing downwards. Okay, but the lift should be perpendicular to the rotor blade. So this is the lift. Now, the thing about the lift being slanted means this. This lift can be resolved into two components, a vertical component and a horizontal component. Okay, so as you can see, a vertical component and a horizontal component. So the vertical component of the lift, let me call it LV, it it will balance the weight. So if it balances the weight, the helicopter will not go up and down. But the horizontal component of the lift, let's call it LH, will propel the helicopter forward. So this helicopter will move forward. So therefore, if you look at the helicopter, how come when it moves forward, it tilts? That is the reason. It is to ensure that the lift is at the component. Okay, it is at a component. It's not vertical. It's at a certain angle so that it has a vertical component to balance the weight and a horizontal component to drive the helicopter forward. Okay, so let's go to the YouTube channel or get some pictures of helicopter on Google and have a look. Okay, so this is what this third lecture is all about. It's about the vector, resolving the vector. So this is a mathematical skill that is very important for many of the 20 chapters in H2 physics. Okay. Yes, so today we're talking about scalar and vector quantities in physics. I'm sure you've come across scalar and vector quantities in physics at O level. Okay, so in terms of definition, a scalar quantity has magnitude only. So scalar, you're only concerned about the magnitude in terms of number. But a vector, you're concerned about both the magnitude and the direction. Okay, so what does it mean? If let's say I have a quantity, okay, let's say I have quantity Q1, Q2. Uh, if let's say Q1 is 3 and Q2 is minus 5. What does it mean? Okay, we're talking about scalar. If Q1, Q2 are scalar, if Q1 is 3, Q2 is minus 5, what does it mean? It only means that they have a magnitude difference of 8. Okay, because the difference between 3 and minus 5 is 8. 3 minus 5 is 8. That's it. But if it's a vector, okay, if now we're talking about vector, let's say Q1 and Q2. Q1 is 3, Q2 is minus 5. What does it mean? It means that Q1, okay, is maybe 3 units in one direction and Q2 is minus 5 in opposite direction because for vector, the negative sign means direction. So the difference in magnitude perhaps is only 2, okay? But because when you add these two together, the resultant is 2 to the right. Okay, if let's say -5 is to the right, if we take the leftward as a positive direction. Okay, so that is the difference between scalar and vector. So scalar only have magnitude, vector has both magnitude and direction. Okay, and but sometimes in the Cambridge question they do ask which of the following are vectors, which of the following are scalars. Now this thing you need to know, okay, it's not something that is derived. For example, force is a vector because force has direction, correct? Displacement is a vector because displacement has direction. But then if you take force times displacement is equals to work done. So please don't tell me that, oh, because force is a vector, displacement is a vector, work done is a vector. No, work done is energy, and energy is a scalar. Okay, so this is what this is trying to say. So whether the quantity is a vector or scalar, you need to know it yourself. Okay, you cannot construct or derive it through formula. Okay, so that's that. So what is the meaning of negative sign in a quantity for scalar and vector? I have already mentioned above. Okay, so now let's go to vector addition. So basically, this is what you see in A maths. I'm sure you've learned vectors in A maths. So when solving physics problem, it's often helpful to replace one vector quantity by a combination of two vectors. These two vectors must of course be equivalent to the given one. Okay, so unlike scalar quantity that can be easily added, because scalar you don't care about the direction, you just care about the magnitude. So scalar quantities, the addition is just add up the number. 1.8 kilogram plus 2.2 kilogram is 4 kilogram. There's no direction associated to weight, sorry, to mass. So there's no direction associated to it. You just add up the magnitude. That's it. But if they are vectors, the direction matters. So if it's vector, 1.8 plus 2.2 is not may not be equals to 4. Okay? So for vector, the only way 1.8 plus 2.2 equals to 4 is if they are in the same direction. 1.8, 2.2, so equals to 4. Same direction plus same direction equals to same direction. Yeah. But if they are not in the same direction, 1.8 plus 2.2 is certainly not equals to 4. So you need to know how to resolve a vector. In A level, there are three approaches. Approach one is accurate scale diagram. Okay, by drawing accurate scale diagram, this kind of things they asked way in the past and they do not ask that anymore. So you don't really need to worry about this. A second method is by calculation using sine and cosine rule of Pythagoras theorem. Okay, so this is a mathematical style of doing. It can work, but it's not always that straightforward. The easiest way is to use the component method. Okay, I assure you that for physics, if you just use a component approach, you're definitely able to solve all the questions. Okay, so let's look at this work example 23. Because it is in the syllabus, we have to still show you how to do it by accurate scale diagram. Okay, by accurate scale drawing. Although really in the past 15 years since there was SARS, since there was SARS in 2003 until now, no, I don't think there's any question on accurate scale drawing. In the diagram below, xy represents a flat kite of weight 4. So there's a downward force of 4. At a certain instant, xy is inclined 30 to the horizontal and the wind exerts the force of 6. Okay, so you can see the 4 down and the 6. Draw a scale diagram to find the magnitude and direction of the resultant force acting on the kite. So basically, 4, what they want is this 4, okay, plus 6, sorry, 4 plus 6. So draw it accurately. Draw it accurately means you come up with a scale. 1 cm is 1 Newton. So the red arrow make it 4 cm, the green arrow make it 6 cm, and use the protractor to accurately get this 30 degrees. So the answer is blue. So after you draw this, the resultant will be blue because red plus green equals to blue. And then you use a ruler to measure how many cm is that. Okay, the corresponding length will correspond to the force in Newton. Okay, so that is the accurate scale diagram way of doing. Okay, uh, this method is thing of the past. Okay, so know this. If for some reason Cambridge tell you that, oh, solve that question using accurate scale diagram, this is the way to do it. But other than that, don't worry too much about it. Okay, now the another method is to use the cosine rule, sorry, sine rule and the cosine rule and the Pythagoras theorem. Okay, so these are the mathematical way of doing. You know the cosine rule, a square equals to b square plus c square minus 2bc cosine a, where the angle a is the angle between the two protagonists, the b and c. Okay, so you can calculate and you can get it. Okay, uh, this is the okay, the angle a is the angle that is opposite the one you want to find. Then this is a, so this is angle a, so this is angle a. Okay, so a square equals to b square plus c square minus 2bc cosine a. You use the cosine rule, you can get this answer straight away. If you use the sine rule, well, a over sine a equals to b over sine b equals to c over sine c. So you see what do you have? You substitute inside, you get the answer. It works if it's a triangle, but the thing about A level questions is that it's not that straightforward, because triangle is always just adding two forces, and then the third one is the resultant force. So three forces, I mean two forces plus the resultant add together, you get triangle. So it works if it's a triangle, but is it really always a triangle? No, most of the time it's not. Okay, so later we'll go through review the component method of doing. Now, so next thing you need to know, what is vector subtraction. So vectors you can only add, but what if you have like a minus b? So you can only add vectors. So a minus b is actually equals to a plus b in the opposite direction. Okay, so that is what it means. Okay, so for example, a minus b, okay, is equals to a plus b upwards. Okay, and then in this case the answer will be this plus this equals to blue. Okay, okay, so vectors you can only add. So if they ask you to subtract, you just change the direction of what you want to subtract with. Okay, so vector subtraction. So this one has been drawn nicely for you. So have a look. A particle moved eastward. Okay, figure 1. If eastward with an initial velocity of 15 meters per second, as shown in figure 1. At the later time, its velocity is 15 at an angle of 60 degrees. So this is it. Now, what is the change in velocity? Always remember, if the question asks for change in velocity, okay, it is always final minus initial. Clear? It is, be very careful, a change is always final minus initial, not initial minus final. Clear? So the final will be this arrow that you can see here, initial is this arrow. But remember, you cannot subtract. Vectors can only be added. So to convert the negative sign to positive sign, you just flip this one. So it becomes brown plus, okay, sorry, brown plus, what color do you want? Red. Oh, it's still, let's put green. Okay, and then the resultant will be blue. Okay, so if it's a subtraction, you just what you subtract with, just flip it over, it becomes a plus, and then you can get the resultant. Okay, work example 25. A ship is traveling east due east 3 meters per second, and it changes course to that. What's the change in velocity? So, ladies and gentlemen, it starts with 3 and it changes to from this to 4 due south. Okay, so what did they want? They want the change in velocity. So change in velocity equals to Vf minus Vi. So 4 minus, this is 4 minus 3. Okay, so 4 minus 3 equals to 4 plus 3 in the opposite direction. Okay, so if you add them up together, uh, I will have this and this, 3 and 4. And so the answer will be 5. Okay, because you can see that they are right angled. So 3 square plus 4 square, the whole thing square root is 5. So the answer is this one. This one. Clear? So it is quite straightforward. Uh, Now, so this one given the following two vectors A and B as shown below, draw the resultant for A minus 2B. Well, A minus 2B. So this is B. So just make the length of B twice. Okay, A minus 2B. That's what they want. And you have to flip it. Okay, you have to flip it. So it becomes A plus minus 2B. So it is this plus this. Okay, there you have it, this plus this, and the resultant, which is A minus 2B, will be this one. Okay, so that's fine. Now the next one. So this concept is a bit it's new recently. It's a thing about relative velocity. Okay, so let's. Okay, in terms of relative velocity, uh, now so you can look at this example. If you're standing stationary in the MRT train, watching the MRT traveling east to west. Since you're stationary, if the MRT is traveling from east to west at 20 meters per second, you look at it that it is traveling at 20 meters per second. But if you're standing on the MRT itself, even though the MRT is moving, what you see of the MRT is as if it is stationary because both the MRT and you are traveling at the same speed. But if you're on the MRT and the MRT is traveling and the person is at the platform, you'll see that the person is actually traveling in the opposite direction and the MRT is stationary. So this is relative velocity. Okay, so by convention, we're using VAB as relative velocity of A with respect to B. So VAB is equals to VA minus VB. You always subtract the observer. Okay, the relative velocity of A with respect to B means VA minus VB. With respect to is always with respect to the observer. Okay, so referring to the above example, the relative velocity of MRT with respect to the station, let's call it VMS, it is equals to VM minus VS. Okay, so so for the other one, the relative velocity of the station relative to the MRT, so we called it station VSM, VS minus VM. Okay, So one is 20, the other one is minus 20. They are vectors. So it means that it is the same magnitude but the opposite direction. Okay. So let's look at this work example 27. This is a recent H1 question. A passenger in a train traveling due north. Okay, train traveling due north. So let's call it VT. There you can see below VT going up. Sees a car traveling due east. Let's call it VC. What do they want? They want the diagram that shows the velocity of the car relative to the passenger in the train. So it is velocity of the car. So it is VCT. Okay, so VCT, because it's relative to the passenger in the train, so you always subtract the one that is relative to. So it's VCT. So VCT will be equals to VC minus VT. So that's how you draw it. Okay, so VC to the right, VT upwards, but since you are subtracting, so you are just adding the reverse of VT. So become VC to the right, and then, okay, let's go VC, and then VT, because it's subtract. So because VT is upwards, but because it's subtract, so you add the opposite direction. So VT downwards. So, ladies and gentlemen, the resultant is blue, VCT. Okay, so that's that. So this work example is to tell you that it is relative to something. So that is the something you subtract to. Okay, you subtract with. Now let's go to this one. Just now we mentioned there are three methods. So it is acute scale drawing, then there's a sine rule, cosine rule, and the third method is a component method. This is the method that you need to know. Okay, this is the universal method, which means that this method of resolving vector you can solve for all situations. So you must know this. Okay, vector resolution into two perpendicular components. So this is called the component method. Now, understand one thing first. If you have a vector, let's call this R, and you want to resolve it. Now, okay, let's draw a few R's, another R here, and you want to resolve it. Then the vector that you use to resolve is always the resultant. Okay, it is always the resultant. So in this case, I can always resolve it to horizontal component and vertical component. So in this case, I call this R horizontal, R vertical. So you can see this red line is of this length. The vertical length of this red line is equals to this vertical, the same height. Okay, and the horizontal length of this red one is equals to this horizontal component, the same length. Uh, you can resolve vectors in various ways. Does it really always have to be horizontal and vertical in that manner? It can also be, let me see, just resolve it any way you want, like this and like this. Okay, so there are many ways to resolve it. It's up to you. So let's look at the example here. So in this case, A is a vector that you want to resolve. So A is a resultant. So the length of A is like this. So the horizontal component will be the horizontal with the same length of A. The vertical component is that. Okay, and the angle here is theta. And if you put this horizontal AX there, and you put the vertical AY there, and you draw in the resultant, you'll find that they form a it is a right angle triangle. So it's actually a something like Pythagoras theorem if you want to know the magnitude of A. So the magnitude of A is equal to square root of the horizontal component square plus the vertical component square. Okay, so this is how you get the magnitude. If you want to know what the angle is, then tangent theta equals to opposite over adjacent, AY over AX. Okay, got it? So this component method is the most useful one. You'll work in all situations. whether there are two forces, three forces, or four forces. Okay, if you look at the work examples, it will help you see easily. Work example 28. A box is put along the floor by means of rope making angle 30 degrees. So this 30 degrees is here. 30 degrees with the horizontal. So the pull of the rope is 80. So the pull of the rope is 80 Newton. So this is the 80 Newton there. Okay. Uh, so calculate the effective part of the pull in moving the box and also the force tending to lift it off the floor. So basically, they're asking you, what is the effective pull in moving the box? Moving the box is in a horizontal direction because with this box move, it moves in a horizontal direction. So they're asking you what is the horizontal component? Well, the horizontal component is simply 80 cos 30. Yeah, is 69. 80 cos 30. And the vertical component is 80 sine 30. Okay, the vertical component is 80 sine 30. So it is 40. So anyway, always remember this. The angle here is 30 degrees. Here it goes again. The angle here is 30 degrees. The component that is attached to the angle, you always do a cosine. Okay? The component that is away from the angle, you do a sine. Okay? Because you see, if you look at the triangle, let's say this is theta, this is, let's say sine. Okay, this is opposite adjacent hypotenuse. So sine theta will be opposite over hypotenuse. Okay, so the opposite will then be equals to hypotenuse sine theta. So as you can see, the opposite, it is the vertical component. Okay, so the vertical component is the angle, is the component that's away from the theta. So always remember, the component away from the theta is sine. The component next to the theta is cosine. So let's look at this one. Cosine theta is equals to adjacent over hypotenuse. So adjacent equals to hypotenuse multiplied by cos theta. So as you can see, the component that is next to the theta, it is cosine. Okay, because adjacent is next to the theta. So remember it that way. Okay. Now, work example 29 is obscenely important because this is the situation that you'll see in many questions. Okay, a slope. So a slope, how do you resolve the vector? You really don't resolve in terms of vertical and horizontal. You always resolve the horizontal is always with respect to the ground. So in this case, her body of mass resting on the rough surface is inclined at an angle. Okay, so it has a normal reaction. So normal reaction n. Let's call this n. Let's color in red. So the arrow is now red, and the friction F. The friction F green. So the friction F green. Okay. Now express the normal reaction n and friction F in terms of mg and theta. Okay. Now the thing is that we know that downward is equals to mg. Okay, we know that downward is equals to mg, and by similar triangle, this one you must know, this angle and this angle are similar triangle. Okay, so the thing about this object is that it is in equilibrium. So if it's in equilibrium, it means that this object do not go up and down I mean, it doesn't move this way or that way, it moves along the slope. So there is equilibrium along the slope. So the red, okay, the red arrow must be equal to uh, this one. Okay, the red arrow must be equal to this one. Otherwise, this object will not be on the slope. Okay, so the red arrow is the normal direction. Let's call it red. And the brown one, okay, or the gold one is actually this component of the weight. Can you see that the angle, can you see the theta is there? So since the theta is there, it's cosine. So it's mg cos theta. Clear? Then the component of the weight that balances the friction, maybe I put another color. What should it be? Purple. Okay. So this component, okay, will balance the friction. This component is to balance the friction. So the friction equals to F. Now this component is a component, you resolve the weight, is a component away from the angle, so it's sine. So this component is equals to mg sine theta. That's how you look at it. Okay. Now a common mistake, okay, a common mistake is for people to resolve it like that. The weight, this is the weight, and then this is the weight, and then you resolve it in this is the horizontal, this is the vertical. So this is wrong, because anything that you resolve is the resultant force. So if you do it this way, look, if you do it this way, okay, if you look at the right angle triangle, this is the resultant instead of this, so it's not. So weight is the one that you resolve, this is the resultant, so you have to resolve it in this manner, not this manner. Okay, because you see, if you resolve it in this manner, after you resolve it, the thing that you use to resolve is still the longest because it's a resultant force. Okay, so you have to resolve correctly. So this is a common mistake at the start, but when you do this so often, you won't make this kind of mistake anymore. So the thing about this component approach, why is it the most useful one? It is because it works whether you're adding 2 forces, 3 forces, 4 forces, 5 forces. Because all you need to do is you get the resultant of the horizontal. Let's say there are 5 forces, A plus B plus C plus D plus E. So what's the resultant? You RX is equals to the sum of all the horizontal forces. So all the horizontal component of A, B, C, D, E, you add together, you get Rx. All the vertical component of A, B, C, D, E, you add together, you get Ry. And then the ultimate resultant will be, as I mentioned earlier, square root of Rx squared plus Ry squared, Pythagoras theorem. So I'll have the magnitude of the resultant, and tangent theta equals to Ry over Rx. So arctangent theta will be equal to arctangent Ry over Rx, and then you get the angle. Okay, so it can be illustrated by this. So this component method always use this. Please, for the A-level syllabus, always use the component method. Please do not use the accurate skill drawing unless the question ludicrously asks you to do that. If not, please don't do that. Okay. Now, work example 30. Use the component approach to find the magnitude and direction of the resultant force acting on the body. So 30 degrees here, 60 degrees. What am I talking about? 3 Newton here, 2 Newton there. So 3 plus 2 is it 5? It's absolutely not 5 because this is a vector addition. So vector addition, what do? Find what Rx is. Find what Ry is. And then you get the answer. So Rx is what? Step by step, Rx, the horizontal component of this one is 2. I want the horizontal component. So the horizontal component, since it's away from the angle, so it's 2 sine theta. There, 2 sine 40. And the horizontal component of 3, you see, is away from the angle. with the angle is 60 degrees. So it's away from 60, so it's 3 sine 60. Yeah. So you add together, Rx will be 3.884. So do the same for Y. So the vertical component, the component that is attached to the angle, you do a cosine. So it's 3 cos 60 plus 2 cos 40. Okay, so Ry is that. So what's the resultant R? Use the Pythagoras theorem, you get this answer. Okay, and the angle will be arctangent Ry over Rx equals to 38 degrees. Okay, it's 38 degrees above the horizontal. Now, so look at this one. Why is it written to, why is the answer given to 2SF? Okay, why is the answer given to 2SF? Because you look at the data they're given to you. This data is 3.0, this data is 2.0. 3.0 and 2.0 are 2SF. So the final answer has to be same SF or one more. So if you give your answer to 2SF, fine. If you give your answer to 3SF, fine. If you give your answer to 1 or 4SF, you'll be marked wrong. You'll lose 1 mark. Okay, so work example 31. Use the component approach to find the magnitude direction of the resultant force. Okay, acting on that kite. So this one is the same approach but slightly different in one thing. Okay, so remember every work example we try to show you something different. So in this case, it is rate 6 plus purple 4. Okay, so once again, this is vector addition. So 6 plus 4 is not 10 because they are not aligned in the same direction. So how to do? Just find Rx and Ry, but have a direction first. Okay, so ignoring the answer that's written there, let's do it fresh. Because I know that the resultant Rx must be to the left, right? So let's take the horizontal left side to be positive. So Rx will be equals to 6 is away from the angle 6 sine 30. Since it's away, I sine it 6 sine 30 plus nothing because this purple has no horizontal component. So that's it. Rx equals to 6 sine 30. Sine 30, please, you don't need calculator. You know sine 30 is half. So equals to 3 newtons to the left. Okay, so what about the vertical component? So vertical component, well, it's up to you to take up or down positive. So if I take up positive, Ry, then it is 6 cosine 30, okay, plus minus 4, because the 4 is downwards. I took up positive, okay, so anything downwards will be subtract, so minus 4. So this will give me 1.2 Newton, okay. So since I have Rx and Ry, I use this to solve, I'll get 3.2 Newton. And then the angle, well, tangent theta equals to Ry over Rx, so I get 22 degrees. Okay, so it's up to you to describe the angle. You can say it is at 112 degrees to 112 degrees to the right, or you can the best 112 degrees anti-clockwise, but the best is draw out the diagram and then put the theta down there and say theta equals to 22. That is the easiest way to illustrate, because remember, a diagram paints 100 words. Okay, so once again, let's look at the values that are given to you. 6.0 Newton and 4.0 Newton, they are both 2SF. So the least significant is 2SF. So your final answer must be how many SF? 2 or 3. Okay, so the final answer here is given to be 3.2 Newton, which is 2SF. That is fine. Okay, so ladies and gentlemen, that's that. This concludes the 3 lectures on this chapter. It really is a basic, simple chapter. It is important, but it is not difficult. Okay, so the next chapter is where kinematics, where the fun really starts. And that is the glory, that is the story of physics. See you.